This shows a standard enterprise network boundary. The edge firewall deflects incoming attacks, but leaves specific gates open for outbound traffic, primarily on ports 53 and 443. Because attackers cannot pierce that perimeter from the outside, they design malware to operate from inside. Once a payload infects a machine, it uses those permitted outbound ports to call home. The firewall allows this traffic because protocols like DNS and HTTPS are structurally necessary. Without them, internal users cannot resolve websites or access web applications. The enterprise architecture inherently trusts these protocols. Historically, security teams tried to block this outbound malware traffic using static lists of known bad IP addresses and hard-coded domains. But adversaries bypass this static approach by rapidly rotating their server infrastructure, automatically shifting their IP addresses and rendering those static blacklists useless almost instantly. To catch modern threats, security operations centers rely on behavioral telemetry. Instead of looking for a known bad destination, they monitor how the internal machines communicate. To defeat modern command and control, defenders must look past the traffic's destination and analyze the specific, measurable irregularities in the query patterns. The most common technique attackers use to evade static blacklists is the domain generation algorithm, or DGA. A DGA relies on a shared cryptographic seed. Both the malware running on the infected host and the external command and control server possess the exact same mathematical formula and seed value. Using the shared seed, the compromised host fires thousands of randomized domains at the DNS resolver. Most don't exist, so the resolver rejects them, generating a stream of NX domain errors. Out of thousands, only one successful query is needed to establish a persistent command channel. While the connection succeeds, the failure leaves a distinct artifact in the logs. The internal DNS server records a localized, massive spike in NX domain errors tied to a specific internal IP address. Standard enterprise web browsing produces a predictable baseline of occasional typos or dead links. A machine generating 1,000 DNS failures a minute represents a severe behavioral anomaly. Security analysts build their detection logic around this exact metric. By querying the SIEM for hosts that show an inverted ratio, where failed NX domains vastly outnumber successful resolutions, they isolate the infected machine. The domain generation algorithm successfully obscures the exact destination of the command server, but its brute force mechanics expose the compromised host through sheer query volume and an extreme failure rate. Command and control is only the first phase. Once the connection is stable, attackers shift to data exfiltration using DNS tunneling. In this stage, the adversary stops using DNS to look up IP addresses. Instead, they repurpose the protocol as a covert transport layer, carrying data directly through the firewall. The malware intercepts sensitive internal files and encodes the raw data into long strings of text, typically using base64 or base32 encoding algorithms. In this DNS packet breakdown, the encoded string is appended and a massive subdomain. Attackers push this string to the absolute 253-character protocol limit. By changing the query type to a TXT record, they force the DNS server to accept large payloads in response. The external server packages encrypted execution commands and malicious scripts into these TXT responses, passing instructions back to the infected host entirely over DNS. To detect this in a SIEM, analysts track the length and entropy of DNS queries. Strings hitting the 253-character limit or featuring randomized text directly violate the enterprise baseline. The second metric relies on record type volume. Analysts isolate extreme spikes in TXT queries originating from a single internal IP address, which rarely occurs normally. DNS tunneling repurposes the protocol as a data stream. Identifying these breaches requires monitoring for high-entropy query strings and protocol limit violations indicating data movement. Extracting these network mechanics requires a robust data pipeline. Enterprise proxies and DNS resolvers continuously feed raw packets into the SIEM, formatted as JSON or CSV logs. This terminal view illustrates structuring unstructured data. Raw CSV strings are ingested and parsed into clean, indexable fields like source IP, destination URL, and action. Analysts isolate variables using eval and split functions against raw content fields, separating the domain name from the user agent and response codes. With the data accurately parsed, they run a stats command, grouping and aggregating thousands of log entries by source IP and query type. Networks generate immense volumes of DNS traffic, so analysts apply a strict exclusion list to filter out known good domains. In the final step, they sort remaining data by event count and internal IP. This surfaces outliers, the machines generating thousands of NX domains or max-length TXT records. Billions of raw events yield results once they are parsed into a schema and measured against normal network activity. There is a modern complication that actively disrupts standard packet analysis, the widespread adoption of encrypted DNS, along with the strict privacy standards of TLS 1.3. When the internal machines use DNS over HTTPS or DNS over TLS, the domain queries are heavily encrypted. If the traffic goes straight to an external resolver, the SIEM dashboards at the network boundary effectively go dark. This diagram maps out the mitigation strategy, shifting inspection directly to the TLS 1.3 handshake. The client machine sends a specific request, the client hello packet. While TLS encrypts the bulk of the handshake, the server name indication, or SNI field, remains in unencrypted plaintext. To maintain visibility, organizations deploy firewalls capable of acting as DNS proxies. These proxy devices intercept the outbound traffic and extract the plaintext SNI data before the connection leaves the network. This creates a comprehensive threat hunting workflow. Security teams can now correlate the internal DNS logs from their own resolvers with the edge proxy's SNI telemetry. Pairing an internal spike in NX domain errors with a stream of highly randomized external SNI strings provides definitive confirmation of an active C2 beaconing attempt, regardless of the encryption layer. By cross-referencing internal resolver logs with unencrypted handshake data at the boundary, defenders maintain visibility. This technical correlation allows security teams to isolate malicious connections even when the primary payload is hidden from view.